Alrighty, greetings again, outstanding students of true physics. I finally gotten most of my video woes solved. I might ask for some help when we get back to school Monday. But anyway, I want to do now for you an example that is like number 5 on set 2. Number 5 reads, resolve a velocity of 65.0 kilometers per hour at 325.0 degrees into its component northward and westward velocities. So again, I will do one that is like that, but I'm not going to do the exact same one. So in our case, what I'm going to do is take a vector that is, what should we do, 75 kilometers per hour at 335. So we'll take, so this is example like 2-5. 2 meaning problem set 2, vector problem set 2, problem number 5. And so we will take a vector at a vector that is, what do we say? Sorry. 75.0 kilometers. 75.0 kilometers at 335 degrees. Just so it's not the same as the one in the problem set. And we want resolve to northward and westward components. Okay, so that's what we're going to do. And so we, of course, will want to put our little compass rose up here. So we've got north, south, east, and west. 0, 0, 0 degrees, or 360 degrees, which will be more useful to us. 180 degrees for the south, 090 for east, 270 for west. Again, since we're doing it analytically, we don't need to put a scale for the vector problem because we're not going to be measuring it to solve it. So the vector is at 335 degrees and it's 75 kilometers. Well, 335, I know some of you will do this, and that's okay. I don't have my snazzy big protractor here at home. And so I'm just going to go, okay, 335, well, 315 is right in between, so it should be about like that. Good enough. Okay, so I'm going to go ahead and put that down here. I'll like, okay, there's my origin, and it's going to be about like that. Perfectly okay to do that. I know it will be like annoying and tension causing for some, but it's okay. So, and it's a straight line, really, a straight line. Okay, and so I'm going to label it though. Always label it because since we are doing it analytically, the label becomes super important because we're not measuring precise angles, and so that way I'll know what you meant even if you got it kind of off a little bit. Okay, that's 75.0 kilometers at 335 degrees. So the vector has been labeled, and that is the resultant, right? That is the vector, the actual vector, and I'm going to be wanting to get the components of that vector. So I'm going to make that clear that that is the resultant vector. That's the actual vector. And just like the gravity vector, remember we had the gravity vector, there's only gravity acting on my body. That's the only force pulling me downward when I'm on the chair, but I can resolve that into a component along the surface of the chair and a component perpendicular to the surface of the chair. Likewise, we're going to resolve this into components, and this is just like the worksheet that we did. Basically, you just go out here, you know, till you get to that coordinate, and then you go up there. However, we have to do it analytically. We have to do it using SOHCAHTOA. So, I'll still draw those in, right? Because I'm going to draw the triangle in here, draw this in. This is a straight horizontal line, trust me. Horizontal line. Okay, so that's one component. It's going this way. And then the vertical component will go up like that. Okay, and this is the westward component, this way, like the negative x. And this is the northward component, or the positive y direction component. And so, I'm just going to go ahead and put my angle in there, theta. Okay, and then I'll use SOHCAHTOA. So this is the hypotenuse. This is the opposite side, because the angle is there. And this is the adjacent side. Yes, if you put the angle somewhere else, you can do it that way too. No problem if you've already done it like that. This is just one way to do it. So, that's my angle. Do I put 335 degrees in there? No, you do not. Okay, that's not 335 is the compass direction. We need the interior angle here for the triangle. So we have to figure that out. We know that this component is going, that's a straight line, really, trust me. Okay? This component is headed in the direction of 270 degrees. We know that. Okay? So this is 270 this way, that's 360 that way, and this is 335 degrees up here, right? And so from 270 to 335, that's what this angle is. It goes from 270 to 335. And so 335 minus 270 would be 65 degrees, right? 335 minus 270 is 65 degrees. So I get theta equals 65 degrees. Is that still on the screen? It is, good. Okay, so that's my angle. And now what I'm going to have to do is just plug in SOHCAHTOA. And so we want to find the adjacent and we want to find the opposite. And so remember that, let's see, we have the hypotenuse and we have theta, okay, which is 65 degrees. And so the sine of theta is equal to the opposite SOH, right? SOHCAHTOA, the opposite over the hypotenuse. And so that means that the opposite side, which we want, right? This is what we're solving for over here. The opposite side is equal to the hypotenuse times the sine of theta. And that's probably how you remember it from math when you're doing the unit circle and stuff, right? That it's, you know, this value is hypotenuse times the sine of theta. The hypotenuse would be the radius in the unit circle. And so the opposite side is equal to the hypotenuse. We know that. That's 75.0 kilometers times the sine of theta, which is the sine of 65 degrees. And so now I just plug that into the calculator. So I have the sine of 65 degrees is 0.906. So I have 75.0 kilometers times 0.906, which is the sine of 65. It's a pure number. And so that's equal to, multiplying those out, I get 67.973. I am allowed 3 sig figs, right? So 67.973 ends up being 68.0. And my units are kilometers. Okay, so that is in the direction north, right? So that is the northward component, or the y direction component, right? So the northward component is 68.0 kilometers. We typically put that up here, right? Put 68.0 kilometers on the triangle, so then we can see that that's an answer that we got there. And then we'll do this one, the adjacent. And so for the adjacent, remember that the cosine, so CAH, so it's the cosine of theta is equal to the adjacent, CAH, and the adjacent over the hypotenuse. And so again, same way we did it here, the hypotenuse, or the adjacent side, which is what we want here, right? We want the component in that direction, this component right here, right? So that is equal to cosine theta times the hypotenuse. I put it in a different order, sorry about that. Okay, and so that's equal to the cosine of 65 degrees times the hypotenuse, which is still 75.0 kilometers. And so that's equal to, if I put cosine of 65, make sure you're in degree mode, get 0.423, 0.423, that's 423 really, times 75.0 kilometers. Note how I keep the units all the way. You should do that too. Okay, and so I multiply that out, and I get 31.696. I get 3 sig figs, so that's 31.7 kilometers. And that is the westward component. Which is like, so that's the component going westward, that's here. And again, we'll put it up here, 31.7 kilometers. And you see my 65 degree angle is pretty bad. Because, right, these two clearly aren't actually to scale. But that's okay. When you're doing it analytically, you know, you try and get it close. And when you don't, as long as it's all labeled, you're okay. And that's it. So that is an example like 2-5.
See you next time.